So thank you very much for the kind introduction. I should begin with, well, first I want to say how happy I am to be here. I've been in Korea now for 1 month almost, since April 1st, and I'm having an incredible visit, and I'm very, very excited by the direction I see things going in science and in mathematics in Korea. And of course the IBS, this new project, is part of that. So I'm also very happy to be here, even though I feel a little like a fish out of water, because I'm not a topologist, even though I was when I was little, but I somehow left the water. So I have 3 apologies, as I said. First, that I'm not a topologist or a geometry, and so I'm not really here. I shouldn't really be here. Secondly, that I don't know how to use machines, and so I'll use this thing, but then you can't see, but then you can see there, or you can't. I hope there are pens, yes. And thirdly, I apologize that I may have to end very abruptly and run for a taxi, because this lecture was scheduled after the previously scheduled one had already been fixed at SMU, and I have to get there, and it's a long way. So I hope I don't have to be rude and leave in the middle. So when I was asked to talk in this symposium, which is not really number theory, I looked for something that is number theory and that is close to my heart, but that was also somehow related. And I found something that I realized in preparing that I won't get to the part that you'll see that it's related, probably. So you have to believe me. This very interesting connection, I think, to symplectic, even to symplectic geometry and topology, which I don't understand, but certainly to many parts of topology. But a little bit you will see. So the theme I took is the dilogarithm function, which is one of the very oldest special functions in mathematics. Well, all of the other special functions, the most important, are all due to Euler, the sine and the cosine and the gamma function, and maybe even the exponential function, and for all that, not quite the logarithm. And the dilogarithm is also due to Euler, so it's right in there with the oldest ones. And it's the function which is originally defined by the power series. Actually, I'm not sure if it was only Euler, maybe some derivators were also involved, or some exchange of letters. It's the function defined by this power series where x is a real or later complex number of absolute value less than 1, or actually less than or equal to 1. It still converges, of course. The sum x to the n over n squared. And of course, the name comes from the fact that if you did the same thing with the exponent 2 being the exponent 1, then you would get the ordinary logarithm, but the ordinary logarithm, as we all know, does not have a Taylor series expansion at 0, but it does have one at around 1, and so if I write here 1 plus x, I get something, and it's a little more convenient to change the signs to get all plus signs on the left. So LA1 is just the usual expansion, which of course Euler knew very well, of the logarithm, and he asked what would happen if you look at Li2. And of course you can imagine Li3, I won't even erase it, well I'll put it here maybe because my dilogarithm is very important. Li3 would be this, and so on. So we have higher polar logarithms, which I'll mention only very briefly, because they have many connections with number theory, but not so much yet with geometry. So we have this function, and it has many strange properties, and the first strange property well, the first one is that it has special values. So, I mean, that's not unusual if you think of the gamma function. Gamma of n is n minus 1 factorial. Gamma of 1/2 is square root of pi. Or if you think of the cosine function, cosine of 0 is 1, cosine of pi over 2 is 0. But this has only finitely many. So I won't quite give you the complete list. Well, there's one trivial one, of course. If I take x to be 0, this sum gives 0. If I take x to be 1, I get the famous number that Li2 is 1, which is therefore the sum 1 over n squared. This is the value at s equals 2 of the function that is now called the Riemann zeta function, but which is of course also due to Euler, who studied it in great detail 130 years before Riemann. And zeta of 2, it was proved by Euler, has the special value pi squared over 6. So by special, I mean something that you can give in closed form. So those are 2 famous values. But now it's very easy, just by changing the sign of x, to deduce that at minus 1 you get minus pi squared over 12. That's kind of the trivial consequence of Euler's formula. But a little less obvious is that if you take a half, now you see the series which converged very slowly, 1 over n squared. Now it's exponential convergence, 1 over 2 to the n. Then you get pi squared over 12 minus, I think, a half, let me check, log squared of 2. But then, as well as those 4, there are 4 more. And I'll just list one of them and put in 3 more because anyway, the board is running out here. So I could have learned it by heart this morning, but I didn't. So if you take the inverse of the golden ratio, square root of 5 minus 1 over 2, then you have a very strange value, which is pi squared over 10 minus the square of the log of the golden ratio. So all of these are classical formulas, but what is really surprising about them is that there are so few, that there are only these 8. As far as anyone knows, there are only these 8. Of the 3 others, all involve square root of 5. It's like 3 plus the square root of 5 over 2 and so on. They're very, very similar. So that's very strange with a function that is just a handful of very special values. And another very strange thing is that it is a rather complicated, or several even rather complicated functional equations. Actually, there's many, and I'll only list 3 of 2 very simple ones and 1 very important one. So, I guess I have another board so I can use it. So the 3 functional equations, well, I'll just write them. One of them says that if you replace x by 1 over x, that the function is essentially invariant up to sign. It changes sign. But in fact, it doesn't quite. There are correction terms, but the correction terms are just elementary. And similarly, if you replace x by 1 minus x, then again it changes sign. And again, there's a correction term, which in this case is plus pi squared over 6 minus log of x, log of 1 minus x. So those are not so surprising. The proofs are completely trivial. You just differentiate, and then the derivative of Li2 is an elementary function. It's Li1, and so you just check that the derivative is true, and you check it at one point. So the point isn't to prove these theorems, but to discover them, or rather to understand what they are trying to tell us. So there are these 2 very simple ones, which involve just one variable, x, and its symmetries, and if you combine them, a group of order 6, which is, we'll come back to. And then there's a much more interesting one, which has 5 terms. So the new one, the important one, is called the 5-term functional equation. Although, as you'll see, it doesn't have 5 terms. It has a few more, but it starts with 5 terms. So, you see, this, if we ignored stupid terms, I mean, just products of logs, this was a 2-term functional equation. Li2 of x plus Li2 of 1 over x adds up to 0. And this, in that sense, is a 5-term equation. You have 5 arguments. So x and y are arbitrary numbers. And then with the 5 arguments which I wrote down, I'll read them out. X, y, 1 minus x over 1 minus xy, 1 minus xy, and 1 minus y over 1 minus xy. And when you add these up, it's essentially 0. But again, I think I won't copy the formula. I'll just put log terms. So products, again, there's a pi squared over 6, and 3 terms now, log of something times log of something else. You know, log of 1 minus x times log of x, that kind of thing. So up to these very simple corrections, you get a 5-term equation. So that's the kind of basic structure of this thing. And I want to explain a little what that means. It means many things. It has sort of a very deep meaning. Before I do that, maybe I should extend my function a little. You see, the original function, I said that x could be real or complex, but it has to be less than 1 for this power series to converge. But then if you remember, I've already mentioned, and it's obvious, that the derivative of Li2 is an elementary function, which is just log. We can write this thing, let me write it to emphasize that I'm talking about complex variables now. So if I have some z outside the unit circle in the complex plane, I could just integrate the derivative from 0 to z, because after all, the function is 0. So the derivative is simply log. Well, remember it was minus log of 1 minus t. So I could just integrate this. But the problem is, of course, that log becomes many-valued when at 0, so you have to make a cut. You have to cut the plane going from 1 to infinity. But then this integral gives a well-valued function. So this is now a well-defined function on the cut plane C minus that cut. But of course, no red-blooded mathematician wants to have a function that jumps. I mean, mathematicians can jump, but functions somehow shouldn't. So you want to do something to make it continuous across this. Of course, you can lift to the universal cover and get an infinitely many-valued function, and that's actually important in some contexts. But it turns out there's something very beautiful. There's a function that was discovered by David Zagier in answer to a question raised by Spencer Bloch, who needed it in the context of homology of algebraic groups. He needed a function that would essentially have the same function equations, and it turns out that the following function is a very good function. It's one-valued. I take the same Li2 of z, and then I add log of absolute value of z, but now there's no problem because absolute value is a well-defined log, times the log of 1 minus z. So up to 7, the second term is Li1. Now, both of these terms make perfectly good sense in the power series expansions in the unit circle where I started. But now it turns out that this function extends continuously to all of C. In fact, it even extends to C and the point at infinity, so to the Riemann sphere. And you get a continuous function, continuous on the whole Riemann sphere. In particular, it's bounded. And I can even tell you the biggest value of z, it's the value at the 6th root of unity, which is about 1.01 so and so, and it's bounded in the other direction by the negative of that. So you get a continuous function which is actually analytic everywhere, because the definition is analytic, except at 3 points where it's only continuous. So that's the story. And this function is a much, much better one. And while I'm on the subject, maybe I'll say the other important modification. I think I can remove the original definition because you'll remember it, I hope. So the other one is called the Rogers dilogarithm. So L for Rogers, now L for logarithm, I guess. All of x is defined as, again, I don't remember the exact normalization without checking my notes. It's Li2 of x plus 1/2 log of x log of 1 minus x if x is between 0 and 1. So if you look at this functional equation, you see that I've chosen that exactly so that up to a constant it's symmetric under x goes to 1 minus x. And then if x is bigger than 1, we use the other functional equation that we want it to be anti-symmetric. So we choose it to be minus L of x plus a constant, which is 2L of 1. So L of 1, of course, by continuity, remember Li2 of 1 is pi squared over 6, and this goes to 0. So L of 1 is pi squared over 6. And finally, if x is negative, then we use the combination of those two functional equations. We put minus L of x over x minus 1. So again, this function now, it's one-valued because I've chosen a branch, if you wish, but it still has very good properties. I'll draw it, and then let me draw both functions. So to draw L of x, I just draw its graph, and the graph looks as follows. It is infinite slope at 1. It is infinite slope at, 0 and also at 1. At 1, it takes the value pi squared over 6. Then it continues with infinite slope, but it then has a limiting value of pi squared over 3. And in the negative direction, it has the limiting value of minus pi squared over 6. So that you see that L also is a function which extends to the projective line. You can extend it to infinity, but now it's no longer a real valued function as we had before. It's only a function with values in multiples of pi squared over 2, because as you go from plus infinity around back to minus infinity, it jumps by pi squared over 2. So we have these two functions which are now both well-defined, and now something very beautiful happens. I won't even attempt to do it on the computer. I could just press a button and everything would change. If I put here D and D and D, well, you can imagine each time, then in all cases, in all of these equations, the logarithmic terms simply go away. In other words, the complicated functional equations with these correction terms become pure functional equations. And what they say formally is that the element in the sort of just if you make the formal linear group of linear combinations of complex numbers, it says that x plus 1 minus x maps to 0, or x plus 1 over x, I did it in the wrong order, excuse me, goes to 0 on the 5-term equation. Also goes to 0. So they're simply in the kernel of this map. And the same is true for D or L. So I can do the same with D or L. And in one case, I'm using here the free abelian group on real numbers, and in the other one here with real numbers and here with complex numbers. But in one case, it's only the values in R modulo pi squared over 2. So it's a kind of a strange thing. Now, if you look at this, and you're a modern mathematician, you feel that this must have a deeper interpretation. There's, by the way, many, many applications in mathematics, including in geometry, for instance, the theory of webs, due to the discovery of Bohl, who corrected the mistake of Blaschke, and there's a whole beautiful story about that I won't tell. But the meaning of this, actually there are two meanings, and both of them, they're related to each other, and they're both somehow very deep. I mean, they're easy to prove. Well, one is easy to prove, one is difficult. But they explain the importance of this function and relate these things. So one interpretation, which was found, I think, only at the first interpretation of all of this, which was found, I think, basically in connection with the theory of three manifolds as developed by Thurston, and the famous notes on Thurston's course, and Milner there has an appendix or a section where he talks about volumes of simplices, hyperbolic simplices. It turns out you can do the following. Let delta be an ideal hyperbolic tetrahedron. So tetrahedron means a simplex with 4 vertices, so it's 3-dimensional. Hyperbolic means it's sitting in hyperbolic space, so here in hyperbolic 3 space. And ideal means, well, this would be a non-ideal tetrahedron. And if I take the usual model of hyperbolic 3 space that I think most people have seen, it's just the upper half space where geodesics are, for instance, vertical lines or maybe horizontal circles or vertical semicircles, then a totally geodesic tetrahedron, an ideal tetrahedron, is one whose 4 vertices are all on the boundary, so in the bounding plane. That's actually very awkward to draw, so one usually moves one of them to infinity, and then what you see is a Euclidean triangle. So you have one vertex at infinity, then these 3 points, here we have 4 points. But these 4 points lie in the boundary of the closure of hyperbolic 3 space, which we know very well is the Riemann sphere, P1 of C. And then we know also very well that the isometries of H3 are just the group SL2, or rather PSL2C, acting on this. And then we also know that given any 4 points, the only invariant under that group action is the cross ratio. So nothing prevents me, if I have an arbitrary simplex, from moving one vertex to infinity, a second one to 0, and a third one to 1. But then I have no choice. The last one is then fixed. And that's the number Z. And so then the volume of this delta is D of Z. So in other words, if I do it this way, it just means in this special case, infinity, 0, 1, and 0, the volume is D of Z. But it means in general, if you have delta in arbitrary position like this, Z is just the cross ratio of the 4 ZI's. So, which is the only invariant of the ideal simplex, because only the simplex is determined by the positions of its vertices, and through it then you can move freely. So that's the first thing. And then if you know that, then these formulas, which look very strange, become obvious. This was a 6-fold symmetry generated by these 2 transformations, and just says that if you renumber the vertices of a tetrahedron, that will change the cross ratio to 1 over Z, 1 minus Z, etc. But it won't change the volume, except that sometimes you change the orientation, and so it will change the volume of the same. And similarly, the last one becomes completely obvious if you have 5 points on the Riemann sphere. Then you can throw out one of them, just keep 4, and then they will bound a tetrahedron, and its volume will be D of Z. But if you sum all of those 5 tetrahedron, the total volume is 0, because together it's just the 0 chain. And so therefore the sum of the 5 volumes is obviously 0. So this thing that looked mysterious now has a very natural interpretation in terms of hyperbolic geometry. And actually that's how I originally got very interested in it. I wrote a paper with Walter Neumann many years ago, studied the asymptotics in Thurston's theory of the volumes of the sequence of manifolds that you get by doing Dane surgery on a through manifold with a cusp. And then Thurston had shown and Jorgensen that you get a sequence of manifolds whose volumes tend from below to the limiting volume. And to analyze that, you used this, and it turned out the whole thing could be analyzed in terms of an interesting potential function. And I won't mention it again, but that's where the connection to symplectic geometry would have come if I'd been able to talk about it. Okay, so now let me come back to the function. So I said that there were kind of two very basic interpretations of this story. So the second one, well, maybe I'll come to it in a second, and I'll first tell another application. But the application, I mean, I originally noticed it, although once I proved the theorem, it was considered a nice theorem, it was published in Inventiones and so on, it was great, but afterwards I realized it was a trivial theorem because it followed instantly from things that are very deep but that were already known, but they only followed with the second interpretation, which I didn't know. So I'll tell first at the level here. So what I noticed in number theory was the following important application, or a very nice application of these facts. So this is kind of an application now to number theory. And the application is to the Dedekind zeta functions of a number field. Now, at a usual conference where I would be, everybody would be a number theorist, and that would be like explaining homology of the manifold. But since here, not everyone is a number theorist, I think most people do know what a number field is and its Dedekind zeta function, but I'll say just in a few words. So the Dedekind zeta function, which is correctly named, it was really invented by Dedekind, unlike the Riemann zeta function, it's a generalization of the Riemann zeta function. If f is q, then it would be the Riemann zeta function. So f is just an extension of q of degree n, but what that means concretely is that f is simply the field that you get by adjoining to q another variable which satisfies a polynomial equation p of alpha equals 0. And the degree of p, let's say p has rational coefficients, or integer coefficients, it doesn't matter, and it's irreducible. It does not have any factors. So if you try to factor it, it simply is one factor over q. Of course, over c, it factors into linear factors by Gauss. So the degree of p is this degree of the number field, and now we write that degree as R1 plus 2R2, where, let me just draw a picture. So in this picture, there are three real roots, so R1 would be 3, and then you have here kind of a pair of complex roots that you can't quite see. So R2 is half the number of complex roots. I mean, there are two R2 complex roots in complex conjugate pairs. So in other words, if you factor P over R, then we know that you can make it linear times linear, again by Gauss, times quadratic, all polynomials over the reals factor into linear and irreducible quadratic polynomials, and I want R1 of these and R2 of those. So obviously R1 plus 2R2 is 0, is n. But now if you're a number theorist, then you automatically look modulo p, where p is a prime, and then you see that p is congruent to linear times linear, a certain number of linear factors, so p modulo p, the big polynomial p of x modulo p, has a certain number of roots, let's call that R1 of p, and then a certain number of quadratic ones, call that R2 of p, and a certain number of cubic, etc. So in general, we'll have the sum I of p will be n for each n, but of course for every prime the splitting is completely different. You get something complicated, and now I can finally tell you that at least it's the product over p. For a finite number p, you have to very slightly modify this, and now for each linear factor, you take the factor just like in the Riemann zeta function, 1 minus p to the minus s. But then for each quadratic factor, you take p to the 2s, and for each cubic factor, p to the 3s, and so on. So it's a product of primes of those products. So this is an absolutely fascinating function, and what was known previously was the Ziegel-Klingen theorem, that if R2 is 0, so that means that you have a totally real field, so the polynomial is n real roots, then remember I already mentioned at the beginning that zeta q of 2 was pi squared over 6. Well, more generally, zeta f of 2 is always a rational number well, actually algebraic because it's rational over the discriminant of f, which in this case is positive. I won't define it, but it's an integer, so this is the square root of an integer, a rational number, times pi to the 2n. So that's a beautiful theorem, and the theorem also tells you that f of 4 is rational times pi to the 4n, etc. So that was known, but that was the only case where you expected at that time to be able to evaluate the zeta functions. And since it's a big theorem in number theory to evaluate L functions and zeta functions, that was kind of a little disappointing. Well, actually, there was a theorem relating zeta functions. I'll come to it a little bit, not an explicit theorem. But now it turns out that you've, for instance, the following theorem. Let me give you an example. So let me take the field q squared of minus 7. So that means my polynomial is alpha squared plus 7 equals 0. So that's an explicit number field. And now it turns out, there are many formulas, but you have the following beautiful formula, which tells you that you can explain and you can express the Dedekind zeta function of this particular field at 2 in closed form using only one new transcendental function, and of course it's self-named v of z, because otherwise I wouldn't be talking about it. Right? So let me give you the proof. There exists, and this was well known from previous theory, unbared variety, there exists a 3-manifold, a hyperbolic 3-manifold. So some quotient of hyperbolic 3 space with volume. Now I may be wrong by a factor of 2, but I'll just pretend, otherwise it's an orbifold. And the volume is 21 over the square root of 7 over 4 pi squared times zeta of 2. This was known, so it's a specific arithmetic manifold, a quotient of the space by some explicit arithmetic group, and it had been known for 50 years how to calculate the volume, and you knew that that volume was a multiple of zeta of 2. And now the rest of the proof is just one word, triangulate. You triangulate that manifold into hyperbolic simplices, and then, well, there's something, and there are vertices somewhere, and the vertices are algebraic, and so you get a sum of volumes, which was dilogarithm functions, log-Wigner functions, at algebraic arguments. And so the same proof gave the theorem that for all f, zeta f of 2 can be expressed. I won't write it down, but there's a power of 2. Well, maybe I should write it a little, because otherwise I was wasting my time writing down all that r of R1 and R2, which I then never used. There's a power of pi, which is pi to the 2R1 over df, and then you have a determinant. Well, I'll just say you have a sum of products of R2 values of d of x where x are in the number field, so the algebraic numbers. So the theorem says it's expressible in terms of d, but somewhat more explicit you can be yet, much more precise. It's like that. And it's essentially the same proof. You can construct another 3-manifold in general with a 3 to the R2 manifold, whose volume then is expressed, is zeta of 2, and then you not quite triangulate it, you divide it into products of simplices, and you apply the same thing. Now, I said that that theorem, which I liked when I found it because it was very pretty, it related the dilogarithm function to values of zeta functions, but actually it was a known theorem in the sense that nobody had ever noticed it, but it followed from known things. And so that's the second interpretation of this whole story, which is a much deeper one. Well, I mean, they're both deep. The one to hyperbolic geometry is deep, and it's very intimately related to this one. So the second interpretation, I could have left the word interpretation, couldn't I? Well, I left the ION, actually. Very clever. Okay. The second interpretation is Algebraic K-theory. So, to any ring, actually to any scheme even, but let's say, and I only care about fields here, so in fields you can associate things called algebraic K-groups. N equals 1, 2, 3, actually even 0. And the only thing you want to know about them, unless you're a specialist, is that you do not want to know the definition, believe me. I've seen it many times, and it will never mean anything to me, and I don't really think it means too much to people who actually work with it, like Krivin, who invented it. It's a very, very abstract definition that shows you that this group exists, but doesn't in any reasonable sense tell you what it is. So the definition is irrelevant, but I'll just give two basic, I'll only talk about two of them. K1 of f is very easy, it's the multiplicative group, and K3 of f is the one I'm going to be interested in. And that turns out to have a very concrete description which is related to the dilogarithm. So how does that story go? Well, the story goes as follows: K3 of f, this is the theorem of so many people. I won't even say, certainly Bloch is the main one who had the concept, but the full proof used all the top experts in Algebraic K-theory, so Suslin, Yakoyev, Levin, also Dupont and Saar, and so on. So the proof is a combination of many things, but the theorem is that this is isomorphic to a group, which I'll try to define at least approximately, called the Bloch group. And the Bloch group is the following thing. The Bloch group is the set of formal elements in some field. But let me just do it for C. And then you can just replace C by any f, but I want to really concentrate on C. So I take finite formal sums with, say, integer coefficients of elements of C. So it's just the Fourier group generated on C. And then there's a condition, and the condition I'll write down, but nobody really understands this condition the first time they see it. You have to play with many examples, and then after a while you see it's very easy to understand. It's completely explicit, and you can play with it on the computer. But don't worry, I'll just write it for me. It's that the sum ni times zi wedge 1 minus zi is 0. This is all taking place, therefore, in the exterior square of C cross in my case, or of F cross in general. But now comes the interesting part, namely, for all x and y in my field, I look at the same 5-term relation that we had. Since I raised it, I'm writing it once more for the third time already. So we divide by these 5-term relations. And if you want to, don't do it now, but when you go home, if you just imagine what z wedge 1 minus c has to mean, namely x wedge y is something that's antisymmetric and additive in each factor, and then just test x wedge 1 minus x plus y wedge 1 minus y plus 1 minus x over 1 minus xy wedge 1 minus 1 minus x over 1 minus x. And two more, you will see that if you just multiply that, you'll get 0, and then you'll kind of understand this condition. But in other words, forget this. This is the interesting part, actually, is the denominator. So you see in particular that my function d now is still well defined on this group. Because I can certainly define it on this thing just by the sum ni d of zi. That's trivial. You can always extend a function linearly from any set to the Fourier group on that set. But the point is that here I'm divided by a big subgroup, but luckily d vanishes on that subgroup, and so d becomes a well-defined function. And as I said, the deeper meaning now is that d of c is K-theory. So if you think about that, you realize, the multiplicative group of the field is one of the basic elements of all of mathematics. It goes down to, back to Babylonian times or something, that you can both add and multiply, and then at some point people discovered the logarithm, and that using the logarithm you can translate multiplication into addition. Now, that's K1. When you go to K3, then it turns out that in some sense you can do the same, but the role of the dilogarithm is now played by the polylogarithm. So that raises two questions that I'm sure you have in your head. First of all, why did I skip 2? Why did I go from 1 to 3? And secondly, what happens for higher n? So let me just say in a few words that story. So theorem Borel, there's two parts. One is that K3 of f has, all Kn of f have the form finitely generated abelian group. And free, so just z to the some rank plus torsion. And some things are known about the torsion too, but let's say if you tensor with q, then it's slightly stronger. It's not just f2 tensor with q, it's like this. And for this rank, I'll just put the rank. The rank in the case of K3, which is this Bloch group, is equal to number R2, which is the number we had before. Remember, f was my number field, and I wrote its degree as n, but I also wrote it as the number of real roots plus twice the number of pairs, or twice the number of pairs of complex roots. So this is always R2, and more generally, this is true whenever n is congruent to 3 mod 4. There's a periodicity, reminiscent of Bloch periodicity. And similarly, the rank of Kn is R1 plus R2. If n is, 1 is an exception, but if n is 1 mod 4, and the rank is simply 0. if n is even. So that's why I left out R2. The even ones aren't interesting from this point of view, and the rank in the case we care about is R2, which is why when I did the Kling-Ziegler theorem, remember R2 was 0, and then you didn't notice any K-theory because there wasn't any. But if I'd taken the field cube squared of minus 7, as I then did, then it's a one-dimensional group, and that's why I have here single products. And the connection there is the second part of Borel's theorem, that there's a natural map. So I'll just put from C, from R. Well, you see, now in terms of the block thing, but he didn't know about the block thing, when he says there's a natural map from Kn of F into R to this power, R1 plus R2, or just R2 or R1 plus R2, or maybe 0, let's take the even case. Well, I might as well take the odd case because it's the only interesting case. So according to this, the rank is either R2 or R2 plus R1. And it says that there's a natural embedding in such a way that, remember, this is a full-blown group of the same rank, so you can take the quotient, R to the this over of the K group. That volume is, up to stupid factors, zeta f of m. This is for all n bigger than 1. So in other words, Borel told us that there is an interpretation of these number theoretical numbers, zeta f of m, as suddenly coming from K-theory, but it was kind of it was a beautiful theorem, but useless for understanding zeta f of m because we didn't know these groups. But in the case of n equals 2, then zeta f of 2 is the volume of this group, which here is the block group, and here it's really easy. If I take the block group, it is isomorphic to this when n is 2, then this map is really easy. It's just the D map, because f sits in the complex numbers, but not just in one way, but in R2 different ways. And so, because it sits in R2 different ways, I can apply the dilogarithm R2 times, and so I get a vector of length R2, and that canonical map is the Borel regulator. Okay, and I should mention your other natural question. One would be, why did I skip 2? And the other is, what happens for bigger numbers? What happens for bigger numbers is that we don't know. We know this, but there's a conjecture that I made many years ago that's partially proved for n equals 3, that these higher K groups are isomorphic to explicit higher block groups that I defined. So there's a conjectural statement like this, and then the role of the dilogarithm is played by the role of the polylogarithm. So the whole thing fits together. Okay, so now I've used up most of my time, but I want to come to what's to me the most interesting connection now, and I'll say it has to be very brief, with both topology and with both number theory, and at the same time topology, and actually quantum field theory and quantum invariance. And the talk that I'll be giving tomorrow, if some of you will be there maybe at the KMS meeting, will be related to this second topic. So I've now come to the second half of my notes, and I have 4 minutes left. Excellent timing. So I will stop speaking slowly. Okay, so the point is that the dilogarithm, I was going to explain why in a few words, but now I won't. LL2, the function, the function dilogarithm is closely related, or it governs the asymptotics of many what are called Q, I won't even write it because my time is short, HG is hypergeometric, Q hypergeometric series. So let me just give you an example first what a Q hypergeometric series is, and I'll take it's a pair. This is the Rogers-Ramanujan identities. It's the most famous, one of the most famous identities in all of mathematics, and certainly one of the most beautiful. So Rogers and then later Ramanujan and then later both of them in a joint paper defined two power series of a very special sort. And this sort is what's called Q hypergeometric. Each term, the nth term, is a product of n terms of a very, very simple sort. So here, the numerator is q to the n squared, the denominator is 1 minus q times 1 minus q squared up to 1 minus q to the n. And the other one is exactly the same, except that in the numerator you have n times n plus 1. And then the identities, which are considered so beautiful, say that this one, both of them, can be expressed as products 1 over 1 minus q to the n, where n is positive, but here you only sum over n, which are congruent to plus or minus 1, not 5. And it's totally mysterious, why 5? There's no 5 on the left. And similarly, the missing ones, plus or minus 2 mod 5, are the expansion for h. Well, one explanation of this, or one part of what's behind this, is this. Let me take a variable z in the upper half plane and set q equal e to the 2 pi I z. Then I can turn these functions into functions of z just by taking capital G of q and capital H of q. But actually I don't want to do that. I want to multiply here by q to the minus 1/60th, and here q to the 11/60th. Okay? So now if you have these two functions, then it's completely trivial. Then if you replace z by z plus 1, you haven't changed q, but you've changed this one by 60th root of unity. And the same thing for h. So it's obvious that both of these functions are invariant under up to a factor under z goes to z plus 1. But what isn't obvious at all is that if you replace z by minus 1 over z, then you get, if I remember correctly, it's sine pi over 5. I don't remember where the 1 is and the 2. Yeah, no, the 2 is here. Sine 2 pi over 5 times g of z plus sine pi over 5 times h of z. And for h, there's an exactly similar formula. So those formulas are very remarkable because it's, of course, very well known, and I think everyone has seen, that the transformations z plus 1, z goes to z plus 1, and z goes to minus 1 over z, give you the whole modular group az plus b over cz plus d, where abcd is a matrix, 2 by 2 matrix, determinant 1, with coefficients in z. And so we get that this thing is always a combination of g and h. So this is what's called, in this case, a vector value, but a modular form, here actually a modular function. So you have this marvelous modularity property, which is somehow behind these incredible identities, but the question is, and that's a deep question, and then I'll end by saying the question and the conjectural, very partial answers. So the question is, what decides whether a given Q hypergeometric series, or there are more general things, is modular? And I'm not going to go into it, but these Q hypergeometric series also come up as quantum invariants of knots and through manifolds, which is another connection to geometry that I'll be talking about a little bit tomorrow. So what decides? And the answer is, well, we don't know, but the answer given by Van and Mann is very partial. One needs, so here it's a given hypergeometric series. Somebody has given you just a series, f of q. One needs that a certain class, psi f, so Mann explains how to associate to a certain Q hypergeometric series a class in K-theory that this vanishes, this torsion, but in fact in C it's actually 0. So he found this utterly amazing example. You have a problem coming from elementary looking number theory, just power series, and you ask, how do you know when it vanishes? And the answer is, you associate to the class in Algebraic K-theory, in K3 of C, of all things, and that class has to vanish. So I'll just give the example that motivated what he said, and then I'll stop. So he looked at the following 3-parameter family. Actually, he looked at a much bigger family, which is still open, but I'll just take the one-dimensional case. There's a k-dimensional generalization. So we just take exactly the function like in Rogers Ramanujan, but I put in the numerator an arbitrary quadratic function. Okay? And then we ask when it's modular. And according to Van der Maan's conjecture, which as I say is much more general, so this special case is now proved, that should mean that the class of Q is 0 in the block group, where Q is the solution of 1 minus Q is Q to the A. So if you look at the two examples we had for G and H, we have A, B, and C. I called it, sorry, capital A, capital B, and capital C. For those two examples, A was 2, B was 0 or 1, and C was either minus a 60th or 11 over 60. Well, but then the equation is 1 minus Q equals Q squared. And the solution is the root of, the golden ratio, square root of 5 minus 1 over 2. And we saw way at the beginning that Li2 of that Q was something very simple. But that means after you correct it by the larger correction, M of Q, this is a rational multiple of pi squared. And the fact that it's a rational multiple exactly means that the class is torsion, because remember that argument, which is connected to the transcendence invariant, that argument is only defined with modular pi squared. And so that functional equation that we had right at the beginning is exactly connected with this. Now, if A is general, you find that the asymptotics of this are determined somehow by Li2 of Q, and Li2 of Q is this element of the block group, and that's somehow what motivated his conjecture. And just to finish this story, his conjecture would imply that a student of his, partially, and I finished, proved that it's true. There are exactly, I could write them down, but time is out, there are exactly 7 cases where this happens. So it's an amazingly rare thing, but in higher dimensions there are many more. So you have non-trivial examples of this incredible phenomenon that in elementary Q-theories is invariant under the full multiple group. That's something you would expect never to happen. It sometimes happens by miracle. There are 7 cases of the miracle here, many more in general, but all of those miracles come from Algebraic K-theory, and they're detected by this dilogarithm function. So maybe I'll stop with that, given the time constraints.
Any